You've been lied to about Jupiter. Most people have the wrong idea about this planet. And honestly, it's not their fault. A lot of what gets taught in school just doesn't hold up. Jupiter is not a ball of gas. Jupiter is in fact a liquid planet. And just beneath those famous cloud bands lies one of the deepest mysteries in the entire solar system. Let's dive in. The first close-up ever captured of Jupiter was recorded in 1974 by NASA's Pioneer 11 spacecraft. And what you're looking at right now is Jupiter's first ever motion picture, a real time-lapse video assembled from images taken by Voyager 1 as it approached the planet in 1979. But here's the problem with these visuals. As breathtaking as they are, they tell us almost nothing about Jupiter's true nature. If anything, they raise more questions than they answer. What is this thing actually made of? How did it get so impossibly large? It's genuinely hard to wrap your mind around Jupiter's size. It's not just big. It's heavier than every other planet in the solar system combined. You could fit 1,000 Earths inside it. To put the scale into perspective, if Earth were the size of a grape, Jupiter would be a basketball. According to the most widely accepted theory of solar system formation, everything began with a massive spinning disk surrounding the newborn sun. A disk made of rock, metal, gas, dust, and every kind of matter imaginable. Over millions of years, particles within that disk collided and clumped together into larger and larger masses. As those masses grew, gravity kicked in, pulling in even more material. Under this model, Jupiter formed when one of those clumps grew so large and so heavy that it began capturing enormous amounts of gas from the disk, and kept doing so for billions of years. If that theory is correct, then deep inside Jupiter, there should be a massive, incredibly dense, solid core, a rocky metallic heart at its center. An alternative theory, however, suggests that Jupiter actually began its life as a colossal cloud of gas sitting just outside the early solar system. Over time, that cloud may have grown so large that it eventually collapsed under its own gravity, condensing into a dense sphere. This is almost exactly how stars form. The only difference being that stars require far larger gas clouds to complete the process. In this case, instead of a star, what emerged was simply a very large planet, which was later pulled into its current orbit by the sun's gravity. If this were true, Jupiter would have no core at all. It would be entirely made up of layered gas, like a giant atmospheric cake. Most of us were taught the first version, that a large solid core formed first and then pulled in surrounding gas to build the planet. That's not an unreasonable idea. It's actually quite logical. But it's not right. The first real breakthrough in our understanding of Jupiter came in the mid-1990s. And what happened was so improbable, so perfectly timed, that it almost sounds like a movie plot. In July 1995, the planet was struck by a comet. This is not a common occurrence. Events of this magnitude are estimated to happen roughly once every 6,000 years. But we were there, and we had the technology to watch it unfold. The comet was called Shoemaker Levy 9. It was a massive chunk of ice and rock hurtling through the solar system at 216,000 kilometers per hour. Pinning down its exact original size is difficult because by the time it was discovered, Jupiter's immense gravity had already torn it apart into several dozen fragments. But even the largest individual fragment was approximately 2 kilometers across. NASA's newly activated Hubble Space Telescope was ready to observe the impact. Except there was a major problem. The comet was going to strike the far side of Jupiter. It would be completely hidden from Earth's view. We were going to miss it entirely. And then came the incredible coincidence. NASA had another spacecraft that was just about to arrive at Jupiter. That spacecraft was Galileo. Named after Galileo Galilei, the astronomer who first studied the planet through a telescope. Launched in 1989 and bound for Jupiter and its moons, Its scheduled arrival was December 1995. As it approached, it was perfectly positioned to watch the entire collision from an ideal angle. What it observed was 21 separate impacts unfolding over the course of 6 days. The largest fragment alone released energy equivalent to 300 million atomic bombs, making it the largest explosion ever captured on camera. As Jupiter rotated on its axis, the Hubble telescope was finally able to see the scars left behind. The impacts had carved massive black marks into the atmosphere, like burn holes punched through the clouds. The debris plumes thrown up during the collisions had shot thousands of kilometers into space and remained suspended above Jupiter for months. This was exactly the scene that greeted the Galileo spacecraft when it arrived. Jupiter's inner layers had been blasted outward by the force of the impact, and the probe flew directly through that expelled material. For the first time in human history, we were seeing what lay beneath the cloud layer that had been observed with curiosity for centuries. The most striking discovery Galileo made was water. A lot of it. And to scientists, that was deeply puzzling. So puzzling, in fact, that an entirely new mission was designed specifically to uncover the planet's true nature. That mission was called Juno. Launched in 2011, it reached Jupiter in 2016 and began unraveling the mystery hidden at the planet's core. This is why so much of what was taught in school is now outdated. The real knowledge about Jupiter has only started emerging in the last decade. Here's what your science teacher didn't know back then. Jupiter is not made of gas. It simply has a thick layer of gas clouds sitting on top of it. All those colorful bands, storms, and vortexes form within those clouds. But that layer is just a thin shell sitting over the planet's true nature. Let's descend through it, layer by layer. In Jupiter's upper cloud layer, temperatures drop below -100 degrees Celsius. Water crystals interact with ammonia, which acts as a natural antifreeze, allowing liquid water to exist in the upper clouds. As those droplets collide with ice crystals, the clouds become electrically charged, triggering massive lightning storms across the entire planet. This supercooled water-ammonia mixture eventually condenses into mushy hailstones, which fall toward the lower atmosphere, melt into rain, then evaporate and rise again. It's a continuous cycle, a strange, unending chemical rain loop on Jupiter. Meanwhile, hot gas jets that feed those violent surface storms extend deep into the atmosphere. The most extreme example is the Great Red Spot. It's not just thousands of kilometers wide, it also extends hundreds of kilometers deep, reaching down below the ammonia rain layer. The clouds within the Great Red Spot are the highest peaks on Jupiter, rising above all other cloud formations. That elevation exposes them to greater UV radiation from the sun, which reacts with the chemical compounds inside the storm and produces that deep, distinctive red color. Imagine a storm cloud 10 times the height of Everest and 10 times the depth of Earth's oceans, and you'd still fall short of capturing the scale of the Great Red Spot. As spectacular as this outer layer is, the average depth of Jupiter's ammonia and water clouds is only about 50 kilometers. Once you drop below the clouds and begin descending into the deeper atmosphere, temperatures start climbing. The source of that heat is pressure. When you compress molecules, their energy intensifies. On Jupiter, what drives that compression is the planet's enormous mass. Pulling all that material downward and squeezing it tighter and tighter, creating conditions where truly strange things begin to happen. The deeper you go, the more Jupiter's gravity amplifies both the heat and the pressure. It's like moving through an ever-thickening fog. Except here, the fog isn't water. It's hydrogen. Hydrogen is the lightest element in the universe, and in an extreme gravitational environment like Jupiter's, it's the only thing light enough to remain near the surface. Every heavier element has long since sunk toward the planet's core. About 1,000 kilometers below the cloud layer, hydrogen gas transitions completely into a liquid state. This is the closest thing Jupiter has to a surface, a liquid hydrogen ocean. the largest ocean in the solar system. So while the planet is wrapped in a thin gaseous shell, it is not made of gas. Jupiter is, quite literally, a liquid planet. But this liquid is nothing like anything we know on Earth. On our planet, hydrogen can only be liquefied by cooling it to extreme temperatures. It boils at around minus 250 degrees Celsius under normal atmospheric pressure. On Jupiter, the opposite is true. The extreme pressure raises hydrogen's boiling point so dramatically that it remains liquid even at temperatures well above 1,000 degrees Celsius. This ocean extends approximately 20,000 kilometers deep, roughly 2,000 times the depth of Earth's oceans. And as you approach the bottom, the pressure and temperature reach such extreme levels that something extraordinary begins to happen. At pressures millions of times greater than Earth's surface pressure and temperatures around 10,000 degrees Celsius, hydrogen transitions into an entirely different state. Metallic hydrogen. This doesn't mean hydrogen turns into a hard, solid metal. It's still a liquid, but it behaves like a metal. Think of the mercury in a thermometer, but millions of times more exotic. The critical change is this. Metallic hydrogen can conduct electricity. Jupiter's immense gravity compresses hydrogen atoms so intensely that electrons are stripped free from their atoms and move through the liquid unrestricted, generating electric currents flowing across an entire planetary ocean. This liquid metallic hydrogen makes up the majority of Jupiter's interior, spanning roughly 40,000 kilometers in depth. And at the very bottom of all of this sits Jupiter's solid core, or at least what we long believed to be a solid core. For years, the assumption was that at Jupiter's center there was a dense, Earth-sized ball of compressed rock and metal. That seemed reasonable. But today we know the truth is far stranger. New data shows that Jupiter's core is fuzzy. It has no clear boundaries. There is no distinct line between the liquid metallic hydrogen and the solid core. The two states are blended together, interpenetrating each other. This diffuse core extends across a region covering roughly half the planet's radius. Scientists now describe Jupiter's center as something like a giant soup, a mix of liquid, rock, and metal, where the usual boundaries between states of matter have dissolved entirely. A zone of chaos where the rules break down. And the most unsettling part, we don't know whether this is unique to Jupiter or a standard feature of all gas giants. Saturn hasn't been studied at this level of detail, and no one can say for certain whether its interior is similar. If Jupiter's fuzzy core is truly unique, the most likely explanation is a massive collision in the early solar system. Perhaps a rocky planet roughly 10 times the size of Earth slammed into it, and the energy of that impact dispersed and diluted the core. This could also help explain how Jupiter grew so large in the first place. It's a plausible theory, but not a confirmed one. Astronomers have tried to simulate this scenario computationally in recent years, repeatedly crashing planets of varying sizes and compositions into a young Jupiter. At first glance, the results seemed to confirm the idea. Yes, the impacts did produce a fuzzy core. But surprisingly, regardless of which scenario was tested, that diffuse core would recollapse within a relatively short time, reforming into a distinct, solid core. So we're left with a strange reality. Jupiter has this fuzzy core, but we don't know how it formed. Everything we learn about this giant planet leads us to more unknowns. How can a planet have a structure like this? What exactly happened in the early solar system? We don't have the answers yet, but that's exactly what makes Jupiter so captivating. A giant riddle hanging in the sky, a cosmic secret waiting to be solved. And one day, scientists will find the answer, and much more beyond it. Until the next video, take care of yourselves.